Today we are going to explore a critical aspect of controlling and optimizing these industrial giant top gas analysis. Understanding what's happening at the very top of the furnace through the gases it produces, providing invaluable insights into its efficiency and overall health. So, why is top gas analysis so crucial? Fundamentally, it's about understanding and controlling blast furnace operation and efficiency. The key is analyzing the gas composition, particularly the ratio of carbon monoxide to carbon dioxide. These continuous monitoring allow us to track the process efficiency, ensuring the furnace runs optimally. The primary indicator we use is called gas utilization or ETA-CO. Definition of ETA-CO represent the percentage of CO gas utilized for the reduction of ferrous burden. Here is the formula: ETA-CO is equal to CO2 divided by CO plus CO2. Now, 100% efficiency indicator. What does a higher rate of CO mean for you? It indicates that oxygen from the burden is removed with less gas and thus less coke, leading to a much more efficient furnace operation. Modern furnaces even measure gas composition across the radius to ensure a good balance between reduction gas and ore. Now, let's connect these to the core chemistry inside the furnace. Hot CO gas continuously ascend and react with descending iron ores, producing iron and CO2. This process is known as indirect reduction. The CO2 percentage in the top gas specifically indicate if this indirect gas reduction is occurring. As iron oxide are reduced by CO, CO2 is formed, directly reflecting the progress of this reaction. On the other hand, high value of total CO plus CO2 in the top gas can be an indicator of increased direct reduction happening deeper in the furnace. So operator need to focus on the CO and CO2 as well as CO part. The amount of carbon used for direct reduction can even be calculated from this top gas composition. Now, many operational variables directly influence the top gas composition and temperature. First, oxygen enrichment. Injecting pure oxygen at the tuer decreases the mass of hot nitrogen rising, which in turn lowers the top gas temperature by about 1.3 degrees centigrade per kg of oxygen injected. And this numerical value is always important, and operators are to aid in memory. This also impact the overall top gas composition and enthalpy. Next is hot blast temperature. When you increase the blast temperature, it surprisingly lead to a decrease in CO2 and nitrogen masses in the top gas per 1000 kg of iron produced. This is because higher hot blast temperature means less gas is needed for heat in lower furnace, resulting in less gas reaching the upper furnace and thus a decrease in top gas temperature, which is always very important to be learned by the operators. Now, various injectant also significantly affect top gas composition, enthalpy, and temperature. For example, pulverized coal injection alters gas composition and temperature distribution, and unburned PC can even be discharged as dust, increasing fuel rates. Methane injection introduces hydrogen and water into the top gas. Hydrogen injection generally increases top gas temperature. However, watch out for large H2O production, which can cause water condensation, erratic gas flow, and burden agglomeration, which subsequently helps in bringing down the uptake temperature, especially in the context of fall in flame due to hydrogen injection and oxygen enrichment to recover the gap fall in flame temperature. Even CO injection into top segment can be used to lower steady state coke requirement, ideally at 930 degrees centigrade to reduce iron oxide. Finally, top gas charging scrap steel or DRI pellets decrease carbon oxidation and consequently reduce CO2 emission in the top gas.